Okay, thank you very much. Thank you all. Thank you all for attending. So this work has been accepted to Usenix 2023 and will be presented in August next summer. And I would also like to thank Yufei that was in a collaboration with him. And so without further ado, let's start. Okay, so malware analysis, basically it's program analysis with the difference that is in the context of an adversarial, within the presence of an adversarial. And as we know, malware analysis today, and as it is program analysis, it's mainly divided between the static properties of the files and the dynamic behavior of the program. So usually, nowadays, when we analyze some malware, we put in a sort of a sandbox, in order to avoid that the malware spreads across, whatever the host and the computers, and that's it. Okay, in this process, so this is the process, and then we have the human. The human are the malware analysts, that they are security experts, that they are the ones that are involved in the malware analysis process. So their work is to examine the software and to classify the software. They have to understand if they are looking at it is a Goodware or a malware, and if it is a malware, which family it does belong to. And so today we will focus on, so the malware analysis, it's a complex, it is a big process, but in this work, we will focus on the human beings, on the malware analysts, that when they are reading the sandbox reports, okay? And in this work, I will use the term report, as a generic term to describe, the reports that nowadays are commonly used are commonly produced by sandboxes, because it is better to have something. As for example, if you think about any run or such websites, they give you a whole general outline of the malware, the properties, the dynamic behavior. So in this work, when I will say sandbox report or report, I will intend to both the output of the static and the dynamic. Okay, humans are very good actually in doing this. The problem is that they cannot scale according to the new malware produced every day. So if you see at this graph, so we have more than 12,000 malware per hour, 3.5 per seconds. So I mean, as if I have to, to analyze the whole process of a malware without digging too much into the reverse engineering task, for me, usually I need, let's say, 2 to 3 hours to exclude, all the signs. So in the meantime, I have 24,000 new malware and this is a problem, and therefore we have to resort, to some automated task. And in the recent years, we are using machine learning, so that is an easy to deploy and scalable solution. And I think you all know how the insane amount of scientific literature that has been produced so far, talking about machine learning. The point is that machine learning works really well if the data set, if the data that you're analyzing, if all the statistic correlations, they do not change over time. But in this case, the problem is that the models can go behind the training data, and the malware authors are aware of this fact, and the malware is a constantly evolving and changing program that in order to evade the detection. And there are several research questions that still need to be answered about how the previous results are robust, and which features really influence the accuracy of classification, because I mean, you often see, this is the new paper, we are producing this new technique using machine learning, and we are using these features with respect to, and in this work, this is what we are trying to answer. So let's try to compare and to understand what humans, which features of Windows malware humans are looking at, and let's compare them with the ones used by machine learning algorithms. And so this is the reason, the research question of my work, in which we are trying to compare the humans with the machines. At the end of our study, we were able to perform an experiment on 100,000 humans, 38 experts. They comes from very famous cybersecurity companies. I can't say the name, but especially from the antivirus companies, academic researchers, and then 72 novices. And with novices, I mean they are all of them. They are students, but at least they have attended a course on malware analysis. They are not completely noob or complete unaware of what they are dealing with. So they have at least a basic knowledge, and this is very important because it means that they have been already trained to perform this task. And then we compare them with a couple of state-of-the-art machine learning algorithms, random forest, and convolutional neural network. So we have chosen, let's say, an old algorithm with respect to a new and recent algorithm. I want to point out, and I will try to repeat this several times during this paper, we are not trying to build something new here. So we are trying to use state-of-the-art without any modification, especially for how the features will be encoded. So we have taken all the review with all the scientific literature, and we have tried to implement the best way to encode the features. So how we performed our experiment? We designed a web-based game. We decided to approach with this gamification approach. The name of the game is Detect Me If You Can. The acronym is DMIC. Our participants have to classify 20 sandbox reports. The design elements of the game are the points and the leaderboard. So the points, it's a way to measure the outcome of the players, and the leaderboard is a way of ranking the players. The point is that our game is completely anonymous. We didn't record any data about the user. The only thing recorded is the interaction with the website. They have to choose a username, so they can provide an anonymous username without revealing anything about their identity. And in order to do not stress the player during the game, the player's position in the leaderboard is only available at the end, so when the game is completed. And I mean, obviously, the goal is that each player has to correctly classify the vast majority of the samples of the reports. The point is that in order to understand which features the humans were looking at, we tried to put this game in a way, and I will describe later, I will give you more detail later. We have tried to push them to use as few features as possible in order to really understand on which features they are looking at. And in order to do this, the players has to buy each feature on each round of the game. What do I mean with features? Static features. Okay. The first two are features related to the VirusTotal reports. And you can think, well, okay, why? But are you already giving the results of VirusTotal to the users? In reality, no. In reality, just 4 samples out of 20s, they contain some VT reports like labels or the submission, the names, submission history. with the name of the file when it has been submitted. And you know, if you are if you haven't read, you know, some VirusTotal report, if you look at the history submission and the name of the files, you can immediately grasp if something suspicious was going on. So, for example, if you look at the Firefox executable, you will always see in the history Firefox.x. Firefox.x is very likely. If you see a malware, you can see, you know, some hashes, maybe the file name changes, so it helps, you know, in order for the classification. We did this, as I will explain later, in order to put some false, positive, true, negative examples in the game. And then we have the signature. The signature, you know, with the P files, you can, it's ala Android, you can certify the author of the executable with, you know, public and private key encryption schema. And then we have the header metadata, so the classic P files information, like, you know, the size of the file and the various dates when the file has been produced. Then we have the sections. The section like, you know, text file or data, BSS, and so on and so forth, with some details like the entropy, you know, and the classical things that you find on the VirusTotal webpage. Then the imports. So the imports, namely the DLL and the function that are imported and requested from the operating system, they are very important because from the imports, you can immediately grasp, you know, what the malware is more or less or is capable of doing. And if you see no imports, really something strange is going on. And finally, the resources. The resources in the P file, you know, you can embed some, I would say some files, icons or things. Again, in the resources, we have the dashes of the files, the file name, the entropy, and no, nothing more. And finally, the strings. The strings, you know, is the output of the strings command. Then we have the dynamic features that are the network traffic, the processes, created, opened, closed, registry, Windows registry interaction, mutexes, created, destroyed. Then this is, you know, mutexes are really, really common in malware. You know, it's like putting a flag on a host in order to understand if the machine has been already infected. This is a very, very common pattern in malware. File system activity and the runtime's DLL. So what does it mean? It means that is the malware at runtime importing some features from some DLL on the machine? And that's it. Okay, the scoring mechanism is quite tricky. I try to go slowly, but I think then I have an image of the game board that will be easier to understand. So at the beginning of each round, so it means that we prompt to a user an empty screen. The player can add new features by choosing them from a predefined catalog of the 15 features I mentioned before. And the player can, you know, let's say, buy and choosing those features until he has gained enough information, enough confidence to make the binary classification. We have 20 samples, 20 sandbox reports, and therefore we have 20 rounds. And we are offering 20 potential points for each round. What means potential? It means that when a player buys a new feature, we reduce the number of potential points. In case of an empty features, we do not reduce the potential point. And with empty feature, I mean, for example, as I mentioned before, we are looking at the dynamic DLLs. So if the malware, if the sample is not dynamically importing any DLL, it means that it is an empty feature. It is giving not any information, or if the sample is not doing any network traffic. So otherwise, the penalty would have been too much hard for the player. In reality, they must buy at least one feature. And why we did this? Because we obviously there are more details in the paper. We want to exclude some participants. For example, someone that just clicked Goodware malware without inspecting any features, or they did not play the game for enough time, So we found someone that never used any feature and played for 3 minutes. It was like Goodware malware, so it was not really playing at the game. And what happens? So let's say that I'm looking at the file system activity, network traffic. I can already spot that the sample is performing something malicious, and I decide that that sample is malicious, and I'm right. I use the 2 features, so I have 18 potential points, and I get the remaining 18 potential points. It means that, otherwise 0. It means that I have to buy at least one feature. We have 20 samples, and I'm making 20 correct 20 correct guesses. The maximum, the highest score is 7,600. Maybe with an example, it's easier. So at the very top left, we have the number of the round. So for example, here it's saying sample 3/20. Okay, the time left, how many features you added. And as you can see here, in green, we have the features that the player has bought, and here we have the rates. So for example, here we have the sections, with the addresses, the size, and the entropy. This is the network traffic. So the sample performed, a DNS request. He got back this IP, and he tried to connect to this IP on this port. These are the remaining available features, and here, when you see this the straight line over a features, it means that the user clicked and tried to buy this feature, but the feature was empty. At the end, when the player had enough confidence and, in his opinion, he got enough information, on the very top we can choose if it is a malware or a Goodware and move to the next round. Okay, here we got the samples of the game. I don't wanna go one by one, but just to give you an idea, over the 20 samples, we have 11 malware and 9 Goodware. I have more or less manually reversed all of them, and I have ensured that there were enough clues for an expert to understand if it was a Goodware or a malware. So just to give you an idea, here the sample number 8, the nanolocker, is a ransomware, and you can understand that it's a ransomware, because it is reading and writing a lot of files. But in this case, sample 17, it is a Goodware. It is Windir stat, is telling you some stats about the usage of the file on your system, and you see a lot of readings. Or is reading a lot of files, but never writing anything. As I've said before, we introduced the output of VirusTotal in order to introduce the concept of true positive and negative and false positive and negative. So what does it mean? It means that, let's take, for example, the sample number 2, that is actually a malware. When the user clicks on, VT detections or label, we are actually reporting the fact that the antivirus engine detects that it is a malware. In this case, true positive and negative are, the good things. And here, instead, we are trying to trick the user. So, for example, this is a very difficult sample because you see a behavior similar to a ransomware, and moreover, the VT, if you click on the VT feature, it is telling you that actually this is a malware. Okay, just to give you an idea of our humans. So all the students, all the novices are students, while we were able to, find a lot of people from industry, researchers. A very interesting fact, we were lucky that we were able to find 5 experts with more than 10 years of experience in malware analysis. Okay, now let's see the results of the humans. Please, we can start to look at the median, because the median and their average, they are quite similar. So it is clear that the experts took less time, and they scored more points. They made more the right answer, and blah 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 and blah blah blah. But as you can see here, for example, the standard deviation of the right answers, you see that there is more variance for the novices with respect to the experts. The experts performed they had a quite stable classification. But what is really, really interesting is that we got a novice that was able to score 19, like an expert. He was we actually know the student, that he was a very good student. So congratulations to him. But this is just data. We had to perform some statistical tests. We performed the Welch test, and on the time needed to complete the game, the final score, and the number of correct answers. So it means that we found a statistically significant difference between experts and novices. And this comes to no surprise. This was just this is an expected result. But for us, what was really strange, you don't see, okay, here, is the number of the feature used by experts and novices. We found no statistically significant difference. It doesn't mean, it means that we don't have enough data, but if you look at it, they used more or less the same number of the features, the total feature during the game. And this is quite strange. We would expect to find some differences. Then the VirusTotal Impact. As I said before, we have the true and false, true positive and true negatives. And in this case, both experts and novices reacted quite well. It comes to, no surprise. The antivirus is telling you something that is actually true, and you tend to believe the antivirus engine. It's engines, because it's a VirusTotal report. But when we are dealing with something false, this is amazing, because, the students made more mistakes, but all the experts were able to deal with the false negative case. And this is even more curious. So in the false positive case, it was a nightmare for the students, for the novices, but also for the experts. So this is just a speculation, is the fact that probably experts tend to be used to false negatives, and probably because I don't know in which mental state they were when they faced this, but they did a lot of mistakes compared to the false negative case in the false positive case. Okay, so now, as I said before, we wanted to see actually what the experts, what our users, they were looking at. So this is how many times the features has been seen by the players, and it is ordered by the by the experts. So if you see here, the orange line is in decreasing order. If you see here the cross, the dash, it means that this feature is dynamic. So there is a little difference. So the novices tend to use more the VirusTotal labels, but in the end, we have tried to see if there is any difference when they classified correctly or misclassified the sample. These numbers, I mean, they're more or less the same. They look like there is no difference between the novices and experts. If you see, the name, the things, the only thing that you can spot from these results is this tendency to use more dynamic features. But I will go more into the details later. So just to spend more words, the experts, they used, the first one was the network activity, the VirusTotal labels, okay, fine. But then the processes and the file system activity. I had time to speak with some experts, and they say that for them, the fact that a PE file has a valid signature is among one of the most important things that they check. If the sample has a valid signature, it's very likely that will not continue the analysis. This is another graph inspired, by the candlestick chart of the finance candlestick chart. So here we have. Let's take for example, sample 12 as sample 1. Let's say that the experts answered correctly. What is this? 45% of the time, and the novices answered correctly 20% of the time. So actually, you can see the delta. The difference of the colors is when the novices answered correctly more times than the experts. So what we can see here, again, the order of the sample is according to the expert's answer. So it means that this was the easiest sample to classify for the experts, while this one was the hardest for the experts. And this is quite curious because in this case, and you can see also the delta is quite high, it means that the experts were tricked from these files, and they answered consistently according to some deception that they found in these samples, while the students probably they answered more randomly, and this is the reason. Now I want to point out, I want to show you an interesting thing is that if you pay attention to this graph and you divide this graph in two, you see that the malware is more to the left of this graph. So it means that looks like that malware it's easier to classify with respect to Goodware. And when I plot this graph, we decided to further investigate this point. Yeah, okay. This is just for information. This was a malware. It was a file infector, and this one was a Goodware game, was a video game library. And if I remember correctly, in this library they were sniffing some network, and this is the reason why the experts were thinking like, or not sniffing, but doing some network scanning, if I remember correctly. So we have tried to understand what's the difference between the classification with respect to malware and Goodware, and we tried to understand how many times experts or novices misclassified malware or Goodware on average. So with experts, we have 1.7 and 2.3, while for novices, we have 2.8 and 3.9. So we performed a Welch t-test, and what we found was that for novices and experts, analyzing Goodware took no longer than malware. So it looks like here, this thing is quite constant. There is no such a difference. But Novices made more errors when classifying Goodware. So probably it means that we need to better train the students. And the reason why, probably because no one taught this to them, or I don't know, we didn't stress this fact enough. We found that experts used more features when analyzed the Goodware, because as a malware analyst, you know, if you're looking at a sample, in order to understand the fact that it is malicious, you just need one sign that it is malicious. On the other hand, if you will classify the sample as a Goodware, it means that you have ruled out all the possible, you have looked at everything in the malware, And this is very important. This is something that we need to teach to the novices, to look on the entire body of the sample before declaring it as a Goodware. Okay, now it's time for the machine learning players. So what we did is that we downloaded 22K samples from VirusTotal, and half of them were malware from 2018 and 2020. The selection criteria was more than 21 antivirus engines, and we paid a lot of attention in order to don't put any families to pollute our data set. So our most frequent families has the 1.1% of occurrences. The half of them were Goodware, and but again we decided, I'm quite sensible to this, and because if you try to pick up your Goodware from VirusTotal, I mean you can find some undetected, unknown sample. And so what we did, we started with a clean installation of a Windows 10 machine, and I have installed all the community maintained Chocolate software. That if you say like that, yes, it's easy. It's just guys, these things, space is not Debian. I had to manually click and fix problems several times each day. It was a nightmare. And then after this operation, we extracted all the executable files present on their disk. So we have a good mixture of Windows 10, Microsoft software, and all new samples. We further refined our Goodware. We submitted all of them. We downloaded the VirusTotal report, and in case they were missing, we submitted them to VirusTotal. We filtered all of the samples detected by more than 3 AV engines, because among these software there are tools like Metasploit, like Nmap, that they are detected as malicious. Nmap, no, but some other hacking tools, they are detected as malicious. So and maybe they can look like a malicious. They can look like malicious, and therefore we filtered them out. So once we created this data set, and again, this is a key point. Now, from now on, I will exclude all the VirusTotal features, VirusTotal related features, because given that we have chosen our malware using VirusTotal, if we use VirusTotal, the machine learning model will overfit on the VirusTotal reports features. So we opt, as I said before, for random forest and the CNN. Yep. And then the validation. Using the validation, we used our balanced dataset. The training dataset was 80-20, so 80% of the Goodware and malware. 5-fold cross validation. And both machine learning players, in the validation dataset, they achieve a remarkable high classification accuracy, right? 0.99. This looks like quite perfect. But as you will see, when we are dealing with unseen data, they do not perform quite well. So let's focus on the errors. And this is a very important thing. the humans had to buy each single feature. So the human didn't have all the features available all the time, while the machines have the all feature advantage. We did not remove any features to the machine learning players. So as we have seen before, the human experts, the average corresponds to the median, achieve a 16 out of 20 accuracy, while the random forest scored 17 and the CNN like the average human experts. So it looks like, I mean, yes, they did good, but they did as the average human beings. The errors the machine made, so both machine learning algorithms, they made a mistake on sample 3 and 17. And this is quite funny because sample 3 connects to a malicious domain, and all the experts that correctly classified the sample 3, no, it's not working. Lost connection, maybe.
You see on the connection, I can say forward.
Yeah, it says I have connection.
Yeah. See you. Yeah.
Okay, sample 3 connects to a malicious domain, and all the experts that correctly classified the sample and look at this feature. So it is likely that the humans saw that domain, they copied it and pasted it on Google, and they immediately found that it belongs to a malicious domain. So here you can see how the humans are able to extend their knowledge beyond the model, something that the machine learning model is not capable of. And then the other errors were sample 12, 4, and 15. And the takeaway of this part is that the misclassified game files, but ML and human subjects are different. So I found no particular difference. But let's have a look at the most interesting thing that probably is the core of our work. So we adopt the SHAP as a model agnostic model. We did not use the recursive feature elimination, the out-of-bag error of random forest, because it inclines to overestimate the importance of high cardinality categorical variables. And let's see the results. And immediately something insane pops up. The first features ranked by random forest and CNN, by the machine learning players, is the last feature ranked by humans. So it looks like the machine learning players were able to immediately find something in the resources that the humans were never looking at it. Then the other point is that you see here, among the first 6 features looked at used by humans, I mean 5 out of 6 are dynamic. Why it is the opposite for the machines. So it means that humans are more interested in the behavior, while for the machines it is important, but still. Okay, we conducted another final experiments, but what if, because so far, the comparison was not fair enough. What if we give to the machine learning players the same set of the features that the best human subject used during the game, trying to understand if they follow, the feature used by an expert human beings, they perform better, worse. So we have chosen the 5 and the 7th most used feature with respect to the top 5 experts records. So we have taken the best experts that played our game. Given that we had to reduce the number of the features, this limited our experiments to 8 samples for 5 and 13 samples for 7. It means that if we had to find some samples for which we have the results of 5 top experts. So it means that they had to look at least on the 5 and 7 features. So again, we retrained our machine learning models, again with the same test settings, five-fold cross-validation, 80-20. Again, with the 5 and the 7 most used features, again, a super good and accuracy, but then with the samples of our games, I mean, they performed worse than random, or random at least. So the human experts, they all classified the sample correctly, and I mean, they really used more than 3 features. So we have taken 7 features, but in the end, the humans they didn't have to use all of them. So they really used more than 3 features in their choices. So they were really, really good. And then as also you can see, the accuracy of the 7 features is even worse than the 5 features. The problem is that here, when we enlarged the number of features considered by the machine learning players, there were a lot of missing dynamic features missing. And this is something that I will insist a bit at the end of the presentation in a couple of slides. Is that we have a problem of how the machine learning is dealing in the presence of missing features. And on the other hand, this is something that the humans do not suffer very much. And the models are more prone to misobservation in case of missing features. Okay, I'm almost done. Takeaways of this work. So, to our surprise, experts and novices, they used the same set of features. The humans and machines, they agree on the importance of 2 features, the network traffic and valid signature. So this is the only agreement we found so far, and it's something that, we have to keep in mind in the future when you're teaching, when you're doing malware analysis. This is something worth looking at when looking at a malware. And then the fact that the resources were ranked on top, and humans last. This is another takeaway for the humans, for the analysts. Hey, guy, please pay more attention to the resources that you will find in the malicious file, because it means that there is something that you are missing, that you are never looking at it. I've manually checked some of the files, and it is actually true. The malware in our dataset, they had a lot of strange resources. They embed a lot of strange resources. The vast majority of them are encrypted resources in their files. And this is my guess. We didn't look at it very carefully, but my guess is that given that the entropy score of each resource were used as a feature for the machine learning that, in case of something with a high entropy, they attributed it to something malicious was embedded in the sample. During the Goodware classification, the expert used more features, and the novices made the majority of mistakes. And therefore, we must teach to the students that in order to classify something as Goodware, they have to rule out all the malicious signs. Then the fact that the experts were able to classify the samples by using less than 1/3 of the available features, and this is quite incredible. They are really. You can really see that they are really experts with a preference for dynamic behavior. And then we have this problem of the missing dynamic features. So the missing observation, that with missing features, For a human, it's not a problem if I see that the malware is not performing any network traffic. For a machine learning model, I mean, probably it means something. It means that in their classification, it is weakening their decision. So one possible road is to produce something semantically meaningful. Reconstructions of missing features can be this like a good feature work, like using autoencoders to reconstruct the missing features. And finally, this work has a significant impact on the human-computer interaction. So what we found, if I would be an analyst looking at a sandbox report, so I would really like to show, to see in the report, first of all the OSINT data. So if I have an IP, if I have a domain, it's really worth giving the human this information, because all the humans that look at that, for example, that malicious domain, it is clear that is something that immediately makes you understand that something wrong is. If you think about it, the VirusTotal graph is exactly what it is giving to you. And moreover, it would be nice to enrich some report with the output of a machine learning classifier that is telling me, okay, for me this is a malware, and for me it is a malware because of this kind of feature, and then the human can focus on the other features and bridging the gap, the cognitive gap that there is with the machines. There are many more findings in the paper. Thank you for your attention.